away, and you only have localized atoms. And the thing that's really cool about this is that just a few years before this experiment was done, the quantum Monte Carlo calculations were able to predict for the first time when this transition should occur, and the experiments confirmed that. If the experiments had been a little bit faster, they would have been able to get a result that had been impossible to calculate by even approximate quantum mechanical methods. It took the development of really sophisticated quantum Monte Carlo techniques to be able to do big systems and see what the transition condition would be. The transition condition is some ratio of the on-site interaction to the tunneling matrix element, because those are the only things that matter in this problem. But here's what I want to emphasize. This is an extremely simple Hamiltonian. There are only two parameters, the tunneling and the on-site interaction. And yet, if you have more than a few tens of sites, you cannot do a brute force calculation. Fortunately, these quantum Monte Carlo calculations are powerful and can do many more sites than that. But if you want fermions, no. So this can't be done for more than a few tens of sites for fermions. And now you see where this is going. If you want to solve this problem for fermions, then what are you going to do? There are no calculational techniques to solve it for fermions, but the atoms can do the job for you. So one of our hopes is we do this for fermions and find out things that we don't know about fermions. There's a question in my talk yesterday about, what would you like to do? What about the Fermi-Hubbard model? And this is the point. If we could do this, we might be able to shed light on high-temperature superconductivity, because some people believe that this Hubbard model will describe high-temperature superconductivity, but no one knows, because we don't know what the solution of the Fermi-Hubbard problem is at zero temperature. That's what we'd like to know, and we don't. We don't know what the phases of the Fermi-Hubbard system are at zero temperature, because it's too difficult to calculate. But it may be, we're still a long way away from that, it may be that we can do that kind of thing. Well, I think that we should probably get to the end of this. Let me just say, there's lots of other things going on in condensed matter, synthetic fields. I talked about that yesterday, a little bit about spin-orbit coupling, which is one of the things that usually pioneered. Superfluid atomic gas analogs to squids is one of the things Gretchen Campbell is pioneering. Spinor quantum phase transitions, I know, is one of the active areas of investigation here. There's all kinds of wonderful things going on, and people all over the place are doing them, including here in this institute in Taipei and other groups all over the world. And if you find this kind of stuff interesting and you're looking for something to do, these people are doing exactly this. They are doing interesting condensed matter related problems with cold atoms. So here is another example of the Mott-Insulator transition that I was telling you about. Making condensates with new kinds of atoms and having different degrees of freedom. So I was telling you about sodium. This is rubidium. There are other kinds of atoms that are possible. All sorts of new avenues of research are opening up, and a lot of that good stuff is happening right here. Part of the future is to go away from just lattices, because lattices are sort of the natural thing that you can do, although lattices are pretty interesting, and go to other kinds of Hamiltonians, and people dream about making Majorana fermions with spin-orbit coupled systems in these atomic systems. So there's all sorts of new directions that one can go in, and the conclusions I leave you with is that cold atoms are a new playground, a new tool that we can use for studying the kinds of things that have been studied by condensed matter physics for a long time. Thanks very much.
his wonderful talk. So now it's open to questions.
And remember, I always ask questions.
Now take the chance to ask him.
And I really enjoy it when other people ask questions.
Can you simulate a four-dimensional optical lattice?
Can I simulate a four-dimensional optical lattice? I don't know.
Because people in Chicago, okay, they are thinking about to simulate the QCD phase transition in the early universe. And that involves the Lamarckian phase theory.
Yeah. And so I know that people have talked about adding a time dimension. I mean, obviously, I could add a periodic time dimension, and then I would have a kind of a Floquet system in addition to my spatially periodic system. I mean, in fact, Floquet is really just block in time domain, so I guess you could do that. But the fact is, I haven't thought about it very much, but I know that some people are thinking, I'm not sure if it's the same idea, but using these lattices as a way of simulating lattice gauge theory.
Yes.
So there, you set up an artificial lattice, and then it's hard to solve. So maybe you can solve one here. So we do have some people within the JQI who have been toying with this idea, but I would say at this stage, it's not mature. But so maybe people elsewhere have a more mature idea about that. But it's certainly intriguing. The answer is, I hope so.
So you mentioned briefly about this, how to understand this ITC problem, this alpha system.
Yeah.
So could you elaborate more about that? Or
Okay.
Is that something to do with the quantum simulator?
Yeah, it's basically a quantum simulator. So let me just say a little bit more about that. We have this problem that no one understands high T superconductivity. We have a wonderful theory of low TC superconductivity. For more than 50 years, we've had the BCS theory, and we don't understand high TC. Some people believe that high TC superconductivity will come out of a Fermi-Hubbard model. But the problem is that the Fermi-Hubbard model, because of the exponential scaling of the difficulty of a problem with the number of lattice sites, as soon as you have enough lattice sites that you might think it's big enough to represent a real problem, you can't do the problem because it's scaling exponentially with the number of lattice sites. So we don't even know what the phases are for the Fermi-Hubbard system. We know what the phases, even before solving it explicitly, we knew what the phases were for the Bose-Hubbard system.
What do you mean phase?
Phases, that is whether there's a superfluid phase, an insulating phase, an antiferromagnetic phase, the kind of things that we know exist in high temperature superconductivity. We don't know whether those phases exist as a result of the Fermi-Hubbard model, which is an extremely simple model. So we're faced with this rather odd dilemma where we have this really simple model, but we can't solve it, and therefore can't know whether a model that simple will solve the problem of high temperature superconductivity. Now, if we could do something with optical lattices and find out that, for example, it doesn't have the phases that we want for high temperature superconductivity, then we could rule out the Fermi-Hubbard model as being one of the things we should think about. Now, that wouldn't be, it's progress, and of course, it doesn't give us the answer. Now, if we find that it does have the phases, then we know that at least it remains a good candidate. So any additional piece of information in this problem is going to be helpful. And it might be that once you find out that, yes, this does undergo the right kind of transition, which we don't know will happen, but let's say it did, then we can start to fool around. And one of the great things about atoms and optical lattices is it's easy to fool around. You can change the interaction strength. I didn't talk about that, but it turns out that for many of these atoms, just by changing the magnetic field, I can change the strength of the interactions between the atoms. I can change the depth of the lattice, I can change the tunneling. So I could change things like the pairing strength and find out whether it's behaving in a way that is analogous to the things that are observed for high temperature superconductivity in nature. Whether it's going to solve the problem, I don't know. I mean, we're certainly hopeful that we'll be able to contribute to this problem because I think it remains remains one of the grand challenges of modern physics. How can it be that it's been this long since we've had high temperature superconductivity and we don't know what it is? But how can it be that we don't know what 95% of the universe is made of? I mean, isn't this an exciting time to be a physicist?
What's the experimental status of making Fermi Hubbard model?
Yeah, well, so I would say the question is, what's the experimental status of making the Fermi-Hubbard model? The real problem is that we need to get the temperature of the gas lower. Because the things that are important in the Hubbard model are, well, there's energy scales, okay? So there's two energy scales. There's the interaction and the tunneling. And you might think that would be it. And as long as you get the temperature much lower than that, you'll be in good shape. Unfortunately not. Because one of the important processes is a second order process in which you tunnel and come back. And that process has an energy that goes like the tunneling squared divided by the interaction. So that so-called T squared over U process is a pretty low energy. And so we need to cool. Remember at the beginning I told you, it's almost like a gas at absolute zero? No, not quite. So, and of course these are fermions, which are harder to cool in some sense, but we can use bosons as a refrigerator, but even that leaves us too high. So there's some ideas about how to go further. So one of the ideas, one of our colleagues, Trey Porto, has come up with this idea. I don't know if it's going to work, but the idea is that you have a bath of bosons around the fermions. And the bath of bosons supports phonons, not lattice phonons, but phonons that are just like sound in the gas, okay? And the idea is that you want the fermions to radiate phonons into the boson bath in the same way that atoms radiate the light into the vacuum, and do laser cooling, except it's sort of sonic cooling, and cool down the fermions by having them radiate into the phonon bath of the bosons. Well, so far it doesn't look so good, but you know, people are clever and trying to find ways around the problem.
I really appreciate that you're making the connection between atomic physics and condensed matter physics. That means that physics will be one discipline, right? Even though you work on different models. I'd like to ask a very provocative question. Because all the models, the Hubble model and the other things that in condensed matter physics, the reason we have those models is because we could not really solve this one-by problem, so it came up with some very simple models, and hopefully those will capture some of the physics. So those models alone have become topics of mathematical physics, or whether that you could treat them alone and then study all the properties and then see whether that would correspond to any of the real phenomena
Right,
observed in condensed matter. All right, so I guess my question is for those models, as you showed here, once we have more and more advanced computational techniques, use quantum Monte Carlo or something, one would be able to solve those models better and better. Now, but on the other hand, in atomic physics, we have this quantum gas theory, have a way to create lattice, you have a way to create different interactions or something. Whether you would be able to see some new models that are not present in condensed matter, and that would create new physics problems there.
Yes, so I hope everyone heard that. I mean, to paraphrase it, are we just a good computer for condensed matter systems, or can we do something really important? And of course, one of the answers is that we don't know for sure that computational methods will be able to solve even some of these simple things, but it's still a good question as to whether we can do something different. And the answer is we certainly hope so. So for example, let's say that using some of the ideas that I was talking about yesterday, or other clever ideas, you could make a quantum Hall system with atoms. particles in the quantum Hall system are bosons instead of fermions, there's a whole different physics involved. So places where you might expect to get strange non-abelian behavior in an electron system happen, but in a completely different area if they're bosons. So for example, if you know about these things, there's the 5-halves step is supposed to have some wonderful properties in an electron system. That happens at 1 in the boson system. So this is rather different. So the fact that you've got a system where you could choose the statistics, and the statistics can make that kind of a change in the behavior of the system, I think that's really cool. And then the fact that that I can make lattices that don't exist in nature, or at least not yet. Remember the talk we had about making new kinds of materials, and materials that nobody had bothered to try to look at, but now you could see, well, maybe that material would be interesting. Maybe we can do that kind of thing with our cold atoms. I really don't know, but I think that the possibilities are so wide that we're sure to find something interesting. Right now, we're just playing around.
What would happen if you move the lattice, the atomic lattice fast enough? I mean, you described the experiment that you did by moving the atomic lattice by different increments, right?
Yeah.
And what's the typical speed you move the lattice, and what would happen if you move it really fast?
Yeah.
I mean, asymptotically, maybe the speed of light. Crazy speed, yeah.
Well, yeah, it's hard to go to the speed of light, but we could go a good fraction of it. Okay, so the question is, what would happen if we moved the lattice a lot faster? So the kinds of speeds that we're moving the lattice at now is on the order of centimeters per second. Okay, so it's really quite slow. The speed, the scale is what we call the recoil velocity, the velocity at which an atom will recoil with the momentum of a single photon, and that's on the order of millimeters to centimeters per second. And we've gone up to tens of times that. So we're talking about maybe meters per second. And doing that kind of thing can produce a lot of really interesting things. So for example, well, let's not go there, but remember what I showed you, that as you accelerate the lattice, the velocity of the atoms gets bigger and bigger. In fact, yeah, let me go to it, because it is so beautiful. You get the atoms having a higher and higher velocity. Yeah, like this. As you go to, but it's a fixed velocity. That is, the velocity that you get is either 0 or 2 photon recoils, or 4 or 6. It's exactly that. There's no uncertainty. This looks noisy just because in the lab things are shaking around a little bit. But the velocity of the atoms is absolutely fixed compared to in integral units of the recoil velocity. So people have used this feature to accelerate the atoms up to hundreds of recoil velocities, and then measure what the velocity is, and from that they get h/m, the ratio of Planck's constant to the mass of the atom. From that you can get the fine structure constant, and from that you can test quantum electrodynamics better than anyone has ever been able to test it. And so there's one of the uses of doing a really fast lattice, and the key thing is that you got to make sure that when you go from here to here, you do it adiabatically. And so there's where going too fast might get you into trouble, because if you accelerate through the Brillouin zones too fast, then you'll leave some atoms behind. You won't get all the atoms being the right velocity. Now, that's still a long way away from going at the speed of light. If you went at the speed of light, or say half the speed of light, what would happen if you had 2 laser beams and one of them was half the frequency of the other? And then that would be an optical lattice moving at a good fraction of the speed of light, right? I haven't really thought about this, but my first inclination would be the atoms would completely ignore the optical lattice, because it would be moving so fast that that they simply couldn't respond. So they would just respond to the average potential that this moving system would have. On the other hand, you might ask yourself, well, what if I got up to that velocity adiabatically? Could I accelerate particles up to some really high velocity? Would this be a new way of making a particle accelerator? I have no idea. But, oh.
You reach a point that the lower wavelength become shorter than the length. The side
Yeah.
was condensed breakup.
Yeah, so certainly all kinds of funny things would happen. And see, here's one of the problems, which is what YT is alluding to. The light has a linear dispersion curve, whereas the atoms have a quadratic dispersion curve. So you can't go too far with this. A honeycomb lattice, sure, absolutely, and people already have. So I'm trying to remember, was it Esslinger who made a honeycomb lattice?
Probably also same stuff.
Yeah, maybe, yeah, you're right, Klaus Senstock did it as well. So yes, and they're looking at graphene-like behavior, absolutely.
Esslinger certainly.
Yeah.
Yes. But I have a impression that Senstock
Yeah.
sound a few different.
Yeah.
A question follow this. You know that you emphasize many experiment condensed matter things you cannot do, but you can do. Now,
Well, not that many. And there's so many more that in condensed matter you can do that we can't.
One interesting topic is quantum spin orbit. Many already mentioned
Yeah.
honeycomb.
Yeah.
Now you mentioned the spin orbit coupling.
Yeah.
Okay? But yeah, quantum spin orbit has been proposed in 2005. But cannot be realized because spin orbit coupling for graphene.
Yeah.
So now you can do that and do honeycomb. I don't know what's the state now.
Yeah,
Can you
so-
see quantum spin orbit?
I don't know.
Oh, you don't.
But since you have the ability to change parameters in ways that are not tied to materials, then it seems you've probably got a better chance. I mean, I've heard people talk about spin Hall. So what do you think?
You don't know what quantum spin Hall, but it's quite relevant to that. Is that there are proposals that actually Ian, one of my previous supervisors, he has an experiment that use spin orbit coupling for atoms to make topological instruments on an atom chip. So it is possible.
Topological instrument.
Right.
Yeah.
So I
Two-dimensional, and then you come with the quantum spin orbit.
I think the one he's trying to make should be a 3D topological instrument.
Okay, 3D
But
you cannot
check.
see quantum spin orbit.
Yeah.
Yeah.
So if you are talking about 2D,
I mean, you may just ask if you say that you can realize honeycomb lattice, then you are not too far away from that.
Well, yeah, I mean, people have made honeycomb lattices, two-dimensional honeycomb lattices, and then I think they just separate them with another lattice, which is similar to what happens in graphene. I mean, you just get one layer, so they can look at either one layer or a bunch of layers that are uncoupled.
But you need a spin orbit coupling.
You need spin-over coupling, but, you know, there's a number of different ideas of spin-over coupling being worked on. So it may be that it can be done. I just don't know. But I think
yeah.
you know more about it than I do.
Well, I think there are too many proposals. Go to look for the literature. So, are there further questions? If not, that's same field again for